anything about it. Okay. I'm actually going to see if I can pull that out of my way a little bit more. I got everything there. Okay. So now that we're all here, we're all recording. Let's take a look a little bit more deeply into the thermo stuff. Let's talk about some definitions about what we need to do. And let's go find my coffee again, because coffee. I love how we start a lecture with me like storming out of the place to go get my coffee so I don't murder someone. Because pretty much there's only 3 people left in the house to murder, and I'm pretty sure they'd find me. All right. So let's see. So, quick note. Let's get over here. Let's do. Quick note. All right. We have something called standard conditions. Now, the standard conditions, some of you may have, thinking back to your ideal gas law stuff, someone may have said that there was standard temperature and pressure. You may have had a high school teacher, or maybe even I've said it offhandedly. Standard temperature and pressure is not standard conditions. So I don't want you guys to conflate the two. If you don't know what STP is, that's totally fine. I don't want to explain it. But if you do remember STP, 0 degrees Celsius and 1 atmospheres, that's a little different than what we consider standard conditions for thermodynamics. As a quick little explanation, standard temperature and pressure for gases was put at 0 Celsius to remove any water vapor that would be in the atmosphere. We don't have to worry about that for thermodynamics, and we're going to do everything at actually room temperature. So standard conditions, we're going to denote standard conditions with a quote not. That's not coming out very well. I think a not is spelled like this, and it'll look something like this. Delta G not, delta H not, and S not. Or delta S not, but we'll talk about that in a minute. When we say that we're at standard conditions, one of the things that we have to note, this means that we're going to be at 1 atmosphere. We're going to be now at 25 degrees Celsius, so we can stay at room temperature. We'll be at either 1 mole or 1 molar conditions. So these are all of the things that are not all of them at once necessarily, but if you have conditions, whatever conditions you do have must be in these things. So if we're talking about a liquid solution, we clearly aren't going to be worried about the atmospheric pressure. We'll be worried about a 1 molar solution. If we're talking about a reaction where we want to figure out how much energy is produced there, we'll be talking about it on a, I can stop my video so you guys can see my face there. We'll be talking about it on 1 mole's worth of material. If we're talking about gases, we'll be doing everything at 1 atmosphere. And the one that is consistent between all of them would be this 25 degrees Celsius. So whenever we see this little knot right here, it's going to imply that we have these conditions. And we're going to keep coming back to this. So I just wanted to quickly define that rule right now. Now, I want to put something up that we have seen probably in the Chem 110. I can't remember if I did it in Chem 120, but I want to recall something here. I want to recall our heating curve for water. Now, I'm going to do water specifically, but remember this heating curve is generic for anybody. So I'm going to go ahead and build this thing. gonna look something like this, where we have down here the heat that we are pumping into the system, and of course the temperature in degrees Celsius here. Now I wonder if I can do this with cool lines here. Oh, this could be glorious. All right, so the heating curve, I'm going to try to draw this really nice. In general, looks like this, where you have a temperature increase, a temperature plateau, another temperature increase, and I'll try to make it a little bit different here. I don't want to imply that all these things are exactly the same. I probably should have actually moved that a little bit. I'll show you here. All right. Now, can I move that? Ooh, I have a mouse. All right. I want to make these nice and sort of tight. Now, this is sort of a generic. I decided to make the slopes a little bit different. And what I probably want to do is make actually this line here a little bit longer, just to show you that they don't have to be exactly the same. I don't want them to be the same because they're never the same. If we label these, down here at the bottom, we have our solid, our ice. Our solid ice. We have our liquid water. And then we have our water or gas. Now, we also have on this transition. So we had the transition going this way. And we had the transition going. You remember that. Which means at this point right here is the melting point, which we know is 0 degrees Celsius. We also had two other transitions on this heating curve. We had the one if we were going forward, and we have the one if we were going backward. And hopefully you guys remember that this is now vaporizing. And condensing. Does this look familiar to you guys? I guess, yeah. Has anyone not seen this curve before? So if Dallas has seen it, then everyone's seen it. Boiling point, which we know is 100 degrees Celsius. Now, the reason why I bring up the heating curve is because we actually have now different zones. So we have a zone right through here, sectioning off each of these areas. I'm going to section it off because what we're going to find is that thermodynamically, each of these regions is governed by a separate equation. Now, so far, as we've pumped heat into a situation, we've said that the Q is MC delta T or MCP delta T. Whereas however much you have, multiplied by whatever its heat capacity happens to be, and the temperature difference over which you are going to do this will tell you how much heat you have to put in and or you could get out of the situation. So in the case of the solid, it is governed by, oh man, I should have made that just a little bit longer. That's all right. This is governed by an MCP delta T for ice. Once you have liquid, it's also an MCP delta T, but this is going to be for water, the liquid. And the gas will also be governed by an MCP delta T now for the gas. Now, if you remember, let me go ahead and change these colors. If you remember, I said that every every material has its own heat capacity. So even though this is water, depending upon its form, its heat capacity will change. So we have to denote whether or not we're using the heat capacity for ice, or the heat capacity for water, or the heat capacity for the water vapor. Now, if you take a look at this, that means that the heat that you have right here for heating up a solid or heating up a liquid or heating up a gas, there's a problem if we try to figure out what is the heat that's going on right here when we're melting or freezing or vaporizing and condensing. How do we calculate that? If we were to use our MC delta T, we have a problem. We have no temperature difference. So if we have no temperature difference, then we would say it doesn't take any energy to do that. And we all know that it does take energy. Well, that is where this guy comes in. And this guy is the mass times something called the delta H of fusion. And over here we have the mass times the delta H of vaporization. Now, we only actually name the quote forward direction because there's no need to do this in the backward case, because it's just a negative sign if you're going the other direction. So they actually just let negative signs take care of which direction you happen to be going. Are you pumping energy in or taking energy out? So the delta H of fusion, or delta H FUS, and the delta H of vaporization, or VAP, those can be used whether you're going vaporizing or condensing, melting or freezing. Now, here's where these come into play. And I just want to point out that in this, these values change depending upon your system. So those values or those numbers would have to be given to you. Do note that the mass or the amount of material you have, the more you have, the more energy it's going to take to melt or vaporize, etc. Hopefully all this is kind of intuitive, but it's very important that we take a look at the fact that over these phase changes, some equations look very similar here with our green MC delta T's. What will change is that heat capacity, that CP. And then we have the different regions for whether or not you're melting or vaporizing, or dare I even say subliming, which is merely a combination of those two. So let's see what this looks like in an actual problem. And I forgot to look something up, so hopefully it's behind me. If not, I'm going to have somebody on a computer look it up real quick for me. What I want us to do is consider the following. And this is where I said what we're going to do is take these things into consideration as we go. Thermodynamics is all about adding up everything that you have going on at the same time. So we're going to have to keep track of everything that's going on. Now, I'm going to need some data here. All right, I need the CP for water is equal to, where we go? That's the 4.186. Where are you? I just want to double check everything.
Yeah, Google agrees.
Thank you. Can you look? Can you look up, because I'm switching all these, so that's going to be joules per gram degrees Celsius. Can you look up the heat capacity for ice and the heat capacity for steam? Because I can do this, I could probably do the calculator on it, but I figure Google probably tells it to us faster.
So ice, it's saying 2.1 kilojoules per kilogram Kelvin.
Is it kilojoules per kilogram?
Yeah.
Okay, so that should be joules per gram. So
Yeah.
37.2 times 18.02. And you said it's 2?
Yeah, 2.1.
Okay. Oops. 2.1. That actually makes a little sense because I have 75 for water and 37 for ice, so it should be about half. 2.1.
And then it has 1.99 joules per gram Kelvin for steam.
And I can go ahead and put degrees Celsius because Kelvin and degrees Celsius, that change is going to be the same. Now, can you also look up the delta H of fusion and vaporization because I still have those in moles? Although I could probably do it here too. You might have something like 108.3.
For the heat of fusion, correct?
Yes. What'd you get?
Saying 333.
Oh, sorry, yeah, 333. And that should be in kilojoules per gram.
That just says joules per gram.
Oh, joules per gram.
Yeah.
That seems odd. Hold on. Let me just make sure here. Oh yeah, 334 joules per gram. All right. So I punched my number wrong. All right. So I'm trying to do both of these. 334 joules per gram. Not kilojoules. And then vaporization.
Okay. Vaporization, it's giving me 40.7 kilojoules per mole.
Yeah, so that's 2259.
It also says 2230.
2230.
Yeah.
Okay, so my calculation was 2259, but we can go with 2230. Okay, so a couple of things I want to note. Now that we have everything in all the same units, a couple things to note about this. You notice that again, I've been harping on the fact that water has a huge heat capacity. It is 10 times that of the metals that we were using last time. But even so, it is still twice the amount of actual ice. One might think that solid water would take more energy to try to move it in a temperature, and it doesn't. It actually takes half the amount of energy to actually go ahead and try to melt or try to heat up a block of ice. And the same thing with water vapor. But more importantly are these guys over here. Take a look at the values for the fusion and the vaporization. They are hundreds or even thousands of times more energy. And that is important because for those who've been with me and those who've seen me or talk about this heating curve, I said it was very important in this heating curve that right here on our little transitions, that the temperature doesn't go anywhere. Because that allows us now to have a situation where if the temperature drops really fast, that's fine. It'll still take a long time for our water to freeze because it requires a lot of energy to go ahead and try to move that thing in one direction or another, which means each of these transitions that we have going across here can either lengthen or shorten depending upon either A, the delta H of fusion, or B, the amount of material you're trying to move from one phase to another. But I do just want to point out that if we're taking into account all of our units, you got to be very careful. Kimchi pointed out that it was 2230 grams or joules per gram. Some people will have it as 2.23 kilojoules per gram. So be very careful on your units. So what I want us to do with these values, though, is I want us to calculate just how much energy would be if we took some ice at -10 and take it up to 110 Celsius. So my problem here is going to be I want to know how much energy it takes to bring 10 grams, just 10 grams, 10 grams of ice at -10 degrees Celsius to steam at 110. Okay. So as I look at, no, I'm going to go ahead and leave that there for a second. So as I look at this, I'm going to go back to that heating curve and look at the different types of governing equations for the amount of heat we're putting in, which ones we're using at which time. Now, I, of course, have made this one so that we're going to use everything. So we are nominally going to be taking our ice, say, from this temperature right here, all the way through all these guys to a temperature up there. So as we look at this, we are going to be looking at going for an MC delta T of the ice. We're going to be looking at doing the M delta H of fusion, the MCP delta T for water, the M delta vaporization, and finally the last MC delta T. So we're going to have 5 different heats that we have to keep track of and add accordingly. What did I just hit? All right. Now, so what are we looking at here? We know that we have the ice. That is an MCP delta T. And we can look at that as the 10 grams times, let's see, ice was 2.1 times 2.1 joules per gram degrees Celsius. And our temperature difference here is, well, our final is 0 minus the -10. And that will give us a number, which Dallas will give me.
No, I just put everything into my calculator at once.
Well, now you're going to do it again.
All right. Wait.
It's 210.
Yeah.
I guess I could have done that, right?
Yeah.
I'm an idiot. So again, taking a look at our units canceling out, 210 joules. So we should end up with a total. So melting is an M delta H of the fusion. Now our mass shouldn't change, so that should still stay at 10 grams. Our delta H of fusion was 333?
334.
So 334 joules per gram. Notice that in this, again, no temperature difference, and that's okay because at the end of the day, we should figure out the actual heat that we're using. And if we do that, we will end up with 3340 joules. Once we have melted it, now we can heat up the liquid. So if we look at the water, we have the MCP delta T for water. I guess I should have put out that this was for ice. We got to keep track of what we're looking at. So that's 10 grams. The heat capacity was 4.186
Yes.
joules per gram degrees Celsius. It's kind of funny now that I'm switching over from the moles to the grams. I can't remember my values. It's kind of funny. I have all the other ones memorized, and I got to memorize new ones. Now the temperature difference here, we are taking it from 0 to 100. So that's the final is 100 degrees Celsius minus a 0 degrees Celsius. And again, our Celsius will cancel, our grams will cancel, and we're left with joules. And so we got 1,000 times that. That's going to equal to 4,186 joules, 4,186 joules. I have to say I'm liking the math on this much better than the mole version. If you could only see my mole calculations. Then we need to vaporize it. So that's an M delta H of vaporization. Again, it's still 10 grams. Nothing here has changed. And the vaporization was 2230. It really takes a lot here to vaporize. That is another one of the key things. If you think about it, just melting ice, you can leave it out and it will go ahead and melt because the ambient temperature is pumping in enough energy to do that. You have to put a lot of fire for quite some time to try to get water to vaporize. It's really hard to do that. So at the end of this, you guys are probably well ahead of me. It's 22300 joules. And finally, for the steam, we have the MCP delta T for steam. And that is 10 grams times, what is that, 1.99?
Yeah.
Joules per gram degrees Celsius. And we're going to 110 minus the 100 degrees Celsius. Those will go away. Grams will go away. And so we get 100 times that is equal to 199 joules. At the end of the day, we're going to add it all up. And what do you get, Dallas?
I got 30,235 joules.
Which is just about what I had when I did it on the molar calculation. Of course, numbers are slightly different and rounding errors can occur. So whether I did it with the molar basis, which is what I have in my notes, or if I do it with the gram basis, it should never matter. Whatever units you are using, if you're consistent, the value should come out. Now, what I want you to do is divide that by 4.186, please. Should be in the 7,000s.
7,222.89.
So 23, so 7,223 calories. That's a lot of calories. Now, keep in mind that's technically 7, quote, calories that you and I would think as far as nutritional calories, right? Because those calories are actually kilocalories. But if you think about it, this is only 10 measly grams of ice. This is essentially, for any of the men that have rings, it's about as heavy as one of your rings you might put on your finger. Ladies, it might be a couple, maybe even 3 of your rings. You just put those on the scale. That's 10 grams. That's not very much ice. And it takes 7 working out calories to take it from -10 to +110. That's a lot of energy. And that's one of the things that makes water so special, is because it does take so much energy to move it from one place or from one state to another, or even within itself.
Hey, Forrest,
Now-
can you scroll up for a second?
Yes. Say it louder.
Can you scroll up for a second?
Oh, thank you. How far?
Just to the H2O.
All of that or more?
Yeah, the H2O, that's good. I'm just wondering why
Yes.
the initial temperature for water is 0.
Where? Oh, okay. Yeah. So that, yes, thank you for asking. So this is one of those things that you want to keep in mind. We're going to go up here to the plot, right? So, and this is not a silly question to ask, because you're going like, wait a minute, what just happened? So as we get on this plot, and hopefully I don't mess it up too much. Well, actually, do I want to just redo it? No, I'll just do it here. So let's just say that we're right here this 0 degree aspect, okay? We started at -10. We went up to melt it, right? We went across. Well, what's the temperature now that our water is starting at? 0. Right? This whole melting kept the temperature at 0 degrees. Then we're going to take it up to 100, which means when we start with the gas, our gas is starting at 100 degrees. Our liquid is starting at 0 degrees. Does that make sense?
Yeah, I was just looking at,
Uh-oh, did my internet?
scroll down a little bit.
This way or this way?
That's okay. Don't worry about it. I got it.
No, I want to worry about it because this is actually important.
I was just I thought there was like some sort of, I thought you were going from the ice, you went 0 minus -10.
Yes,
Well, I didn't-
because we are going from -10 to 0. And it's always final minus initial.
Okay. I wasn't sure if that number was supposed to go into the initial for water. I was just a little confused.
Oh, because, and that's why I said this is actually a very good question, because one of the common mistakes that happens is people will go like, oh, well, I started at -10. Well, yes, you did for that area. Just like when we're doing titrations and we have the first region and the second region, once we get to the new region, you quote start over. And so is we started at 0 or -10 and went to 0. Okay, well, now my new starting is 0. Now I get, you can't see my, we started at -10, we went to 0. Our new starting is 0. Now we're going to go to 100. Our new starting is 100. Now we're going to go to 110. It makes no sense to say, well, we started at -10 for the gas, right? So every time we move to the new phase, we essentially have a new starting point for the temperature.
Got it.
If not, we can talk about it a little bit later if you want. Oh dear. I got rid of my line. Stop it. Want to fix my line here real quick. All right. Now, let's take a look at a little bit more of these. Okay. Let's do something a little more intricate and a little more fun, and one that we have to keep track of stuff a little bit more. All right, this here is, I have 250 mils. I have a 250 ml glass of water at room temperature. I'm going to add 4 ice cubes that are 15 grams each. They're at -10. And I'm going to ask, how cold is the water going to get? Okay. So let's do another one here. We have a dying professor. We have a 250 milliliter glass of water. Yes. We add 4 15-gram cubes of ice at -10 degrees Celsius to it. How cold will the water get? Okay. Man, sorry. Somebody got the cyanide in the coffee. All right. Now I'm going to note for Dallas. Ignore the environment. We're only going to focus on these two things. Okay. Some values that we're going to need. We're going to need the heat capacity for water, and that's 4.186 joules per m degrees Celsius. We're going to need the heat capacity for ice, and that was, I think you said 2.0. No, heat capacity of ice, yeah, that was 2, right?
Yeah.
2.1. Thank you. 2.1 joules per gram degrees Celsius. And we're also going to need the delta H of fusion. We're presumably going to melt the ice. What is in my
334
Man,
joules per gram.
something is in the air. I don't like it. Thank you very much. Now, when I do this problem, one of the things that I want to be very careful of and careful to do is to monitor everything that I'm going to do to this thing, everything that's going on. So sometimes I like to draw a picture. So here I have my glass. Put my little water in here. And I'm going to go ahead and draw myself some ice cubes. All right, and those things are going to go in. So I know right here I have 250 milliliters of ice, which are we all big boys and girls and just say it's 250 grams? Dallas, just say yes. I have 250 grams. It is at 25 degrees Celsius. Here I have now these 4 ice cubes. Is a total of 60 grams of ice, and it is at negative 10 degrees Celsius. And those guys are going to go in. The question is, what is that final temperature? Now, if I can, I draw a cute little picture of it. If I can't, I will do the following, and that is I want to note what is happening to each piece of the system. So I have 2 things here. I have ice, and I have the actual liquid water. So we need to ask ourselves what's going on to each of these pieces of our system. And I'm going to start with the easy one. And I'm going to say, Meng, what is the water going to do physically? Wait, is everyone here? Normally she pops in. Am I still broadcasting, guys?
I can still hear you.
We're still there? Okay. Well, if Meng is a little shy, how about I go to Kyra? What's the water going to do in this situation?
The water is going to become colder from the ice.
All right, so it's going to cool down. All right, so that is going to cool down. Now, what is the ice going to do then? Kyra, keep going.
Would the ice warm up a little bit from the water?
Okay, so the ice warms, so it's going to heat up. Then what's it going to do, do you think?
It'll melt in the water and it'll create more water.
Okay, and what's that water going to do then?
If
If we only melt it, let me ask this to Chef. Chef, if we only melt that water, what's its temperature? Chef, if we only melt the water, if we only get up there to melt it, what is the temperature of that water now?
0 degrees.
That's right. So, Kyra, is it going to do anything else?
no, because the temperature will remain in the transition.
It will actually heat up again. Unless you think that 4 ice cubes is going to freeze all of that water, right? This is where keeping track of what might be happening is very important in thermo. Is you got to think about the systems and what they might do. Now, sometimes you think that they'll not do something, it turns out they do, or you think it's going to do something, it turns out it won't, and you'll see that when it comes out in the math. When it comes out in the math, you're like, ooh, why am I getting like, I have to pull heat out in order to heat it up? That's kind of weird. So you'll see that, and maybe we could do this problem twice, once the full-blown way, and then once the Kyra way, and that is, I'm not going to consider it heating back up again. But I'm going to start it out with the real way. So what we have is the ice is going to go from -10 to 0, right? So this is now the -10 to 0 situation. I'm going to go ahead and just, it's going to melt, right? And then it's going to heat up from 0 to whatever that thing is going to go. The cool down means it's going to go from 25 down to which temperature? And it's these two guys right here that are going to be the same temperature. That's how we're going to know where we're going. So if we look at the ice, and I'm just going to go ahead and do the ice in red, even though it's kind of weird to do that. If we look at the ice is going to go through an mCp delta T for ice. It's going to do an M delta H of fusion, and it's going to do an mCp delta T, and I'm going to go here, icy water. I'll just call it, yeah, I'll just keep it called an icy water. So that's what the ice is going to do. The water is merely going to do an mCp delta T for water. So these are the two situations. Now, I've written them out separately because we know that one is going to give to the other. So the Q of the ice equal to the Q of the water, the heat, right? So my question is, which one of these is positive and which one of these is negative? If we remember,
Ice is positive.
The ice is going to be losing energy.
What?
And so if the ice is losing energy,
Why would
it's
the
going to
ice
have
be
to
losing energy?
negative.
Isn't that ice gaining energy?
Oh, sorry, no, Dallas, you're right. Sorry, Dallas, you're right. The water is losing the energy. The ice is gaining the energy. I actually did that backward in my brain. And this is why I say, and it's you have to be very careful here. The negative signs matter. And if there's one thing that gets people, including myself, in trouble, it's not putting your negative in the correct place. Okay. So let's take a look at what we have so far. We have the MC delta T for ice, delta H of fusion, and again for the icy water, we can start plugging in some 60 grams. And I'm going to go ahead and put everything here in a bracket. We have 60 grams times the ice, which was 2.1 joules per gram degrees Celsius, and its temperature difference, which we already know is going to end at 0 and it's going to start at -10. To that, we're going to add that 10 grams that's going to go at that delta H of fusion, which we say is 334 joules per gram. So far, all we have here are numbers. And finally, we have that, oh, sorry, not 10 grams, 60 grams of ice, sorry. Then we have our 60 grams of ice times now the heat capacity of the icy water. Well, that's just the heat capacity of water. So 4.186. Now I'm going to write this actually down below. So we have it. So that's 60 grams times 4.186 joules per gram degrees Celsius. Now we have our final temperature, which I'm going to go ahead and put in purple. Our final temperature minus our initial temperature, which, Chef, what's our initial temperature of the icy water?
-10. 0.
Right now, and the reason why I keep coming back is I want to keep emphasizing we have melted it, right? We already took it from -10 to 0. So that's now where this icy water is going to start. You can't have icy water, liquid water at -10. So all of these clues I want you to keep in your mind as we go through this. Okay, so I need the first thing here calculated for me. And the second
1,260.
as well. Say it again, Dallas.
1,260 for the first,
Okay.
and 20,040 for the second.
20,040 joules. And now, Dallas, if you could, take this 60 times 4.186.
That would be 251.
251. And I want to point out that this is going to be joules per degree Celsius. I'm not going to multiply it by 0, which I could if I wanted to. But clearly that's going to be a 0. Let's look at the water. So the water here is the negative, and that is the mass times Cp. Say it.
Should you put the TF at the end of that, or is it not?
Oh, thank you. Thank you. Yes, TF. Thank you. The water is our 250 grams. Times our 4.186 joules per gram degree Celsius. And we now again have our final temperature, TF, minus our initial temperature of 25 degrees Celsius. So here we have our ice. Oops. And here we have our water. Dallas, can you give me 250 times 4.186?
1,047.
1,047, and that's going to be joules per degree Celsius times our final temperature. Notice that I've kept that negative sign and distributed it through. Can you multiply that 1,047 times 25?
26,163.
And that's now just joules. Okay, so now we just have to equate these two. So I have my 1260 joules plus 20040 joules plus this 251 joules per degree Celsius times my final temperature is equal to, I'm actually going to move that over here. I'm going to need that room. This is going to be equal to negative 1047 joules per degree Celsius times our final temperature. Plus 26163 joules. Working on the algebra skills. Now, it doesn't necessarily matter which way you do this. You can solve it how you want, but I want to keep everything positive. So I'm going to take and combine my like terms this way, which means I'm going to pull all of my other joules to the other side. Dallas, can you do my 251 on my 1047 for me?
251 times. Oh,
What is that? 12,
yeah. That's going to be
1298.
1297. Yeah, 1298.
Okay, joules per degree Celsius times our final temperature. And that is going to equal to, take your 26163 minus
4863.
Thank you. 4863 joules.
Yep.
So our final temperature is going to be
3.7.
3.7 degrees Celsius. You know what I like about that, Dallas?
Is it the same thing you got?
Oh man, it's the same thing I got when I was using the different values. And again, I just want to point out that it shouldn't matter as long as you keep track of your units. You keep track of your negative signs. It should A, work out, and B, make sense. Does 3.7 degrees Celsius make sense, Miss Ramirez?
Yes, it makes sense.
4K. That means why?
Hold on, let me figure it out. Because the water cools down, so the
Okay.
temperature gets higher.
Wait, the water cools down and what?
Because it starts from negative 10 degrees. So since the water starts to cool down, it becomes 3.7.
Sort of. You're on the right path. This makes sense. This makes sense because we expect the water to cool down. And I might even say, and in parentheses, and the ice to be gone.
Forrest.
Yes.
I don't know if it's like just me, but it just seems like the water like drops in temperature a lot. Is it just because it takes a lot of energy to melt the ice?
That is correct. And I mean, if you think about this, you go to your fast food joints, and if you ever pay attention to your cups that you get from them, there are these tiny little black marks on the side. So I'm thinking like my McDonald's cup. There are two spots that they have marked on their cups, one for little ice and one for a lot of ice. So when and then later on, they actually have a button in many places, in many McDonald's, where you either hit it once or you hit it twice. When you hit it once or hit it twice, you actually fill to that mark. And basically, it is their way of saying, if I fill to that first line, I will give a person essentially 30 minutes worth of cold drink to suck it down. because it's going to take that long for their soda machine or their soda they put in there, plus the ambient temperature, you know, ostensibly, to melt all that ice. But in this case, we didn't really have, you know, half of our cup or a third of our cup full. We only tossed in 4 little ice cubes. Okay. So if you think about it, 250 grams is essentially a cup of water. You have 8 ounces of water, and you put in only 4 little ice cubes. We expect that rather rapidly in some respects, that those 4 ice cubes are going to melt, but it is going to take a whole heck of a lot of energy to do that. Now, since we only have 1 cup's worth of water, which really isn't that much, it's going to have to pump a lot of energy into that. So its temperature is going to drop dramatically. Again, if I had more water, right, if this were like a 2-liter jug of water, 4 ice cubes isn't going to do anything to it. But since we're kind of close on the masses, and because it takes so much energy to do that melting, yeah, that water is going to give up a lot of energy to do that. Now, I do want to point out that if Kyra had her way, okay, and we did not melt the ice. So I'm gonna throw you under the bus here, Kyra. You ready? All right. What if we followed Kyra, followed Kyra's advice, and she said that the ice was just going to heat and melt. And of course, the water was going to cool. Notice we are missing, this is going to be missing now. We're missing that last little bit.
Then the only possibility would be 0 degrees.
That is correct. So issue number one, the cup of water would have to cool to 0 degrees Celsius. It would have to freeze.
Not necessarily.
Well, okay, yeah, you're right. You're right. I misspoke there, Dallas. You're right. It would have to cool all the way down to 0 degrees Celsius. In which case, we have no final temperature to look at. Issue number 2 is if we look at the values here, we're going to have a problem. Okay, so what I'm going to do is go up here. The first 2 numbers here in red, the ones that I've circled up here, you can't see my pen, but the ones right here that I circled, that would be the total energy we had, and we would be expecting this thing to cool down. Watch what happens to the math. So Dallas, can you keep track of that 20,040 plus the 1260, please? What's that going to be?
20,040 plus 1260.
Mm-hmm.
Give me just a second. Uh, 21,300.
All right, so we'd have the 21,300 joules is equal to, and then we just pull down the stuff we had from the water. Remember, we're going to get rid of this guy because that guy doesn't exist anymore. We said it never heated up. We got the negative 1047 joules per gram times our final temperature plus our 26,163 joules. Okay. Now, if we go ahead and subtract those over, so I'm going to pull this over, I get the 1047 joules per gram times my temperature, or joules degrees Celsius, sorry. And subtract those over, Dallas, what do you get?
Uh,
The 26 and the 21?
4,863.
Okay. Please divide that out. What's our final temperature?
4.6.
4.6 degrees Celsius. Now, while this still makes sense, it is actually denying the fact that the ice would actually have to heat up. If you said that it just melted, then how did that 60 grams of ice suddenly become 4.6? If the ice only melted, meaning stayed at 0 degrees Celsius, how is it magically 4.6 degrees Celsius if it didn't heat up? So you see, if you think about the systems you're looking at, at the end, it should all make sense. While it does make sense that the water would cool down, sure, goes from 25 down to 4.6. Whether or not you know that that's an okay number, you at least know that it cooled down. Okay. But if you said that the ice only melted, it would have to still be 0 degrees. We have a discontinuity here, right? We can't have two things at two different temperatures if we are saying what is their final temp. Their final temp cannot be different. Does that make sense?
Yeah.
Yep, I got it.
Okay. Yes?
So I do have a question. Now, when we did the thing and we did everything correctly and stuff, we ended up getting pretty close to 0 degrees. I have to imagine it wouldn't take that much ice such that, the final temperature, not all the ice melted.
Yes, there are circumstances where,
Yeah.
And I've done this in the past for a homework problem where I've said, you dump this much ice into something and what happens? And, oh, sure enough, it looks like you actually froze the water you were putting in there. I have a question. Go ahead.
And so if the situation was such that the final, energy was going to be in that freezing point where not all of it's ice, not all of it's water, but not knowing that ahead of time, we still assume that some of the ice is going to heat up, melt, and then heat up more. How does that
Right.
end up coming out in?
So what'll happen with that? This is a good question, Dallas, because again, we are starting to make assumptions about our systems and then seeing if the math plays out. So again, Kyra made the assumption, thank you, Kyra, that all we did was heat it up and melt it. Well, if we do that, we find that while the ice should have stayed at 0 degrees, right? If the ice stayed at 0 degrees here, then our water would have to be at 0 degrees, but it's not, right? It's not matching up. Does not match. That would be your first clue that, hey, something is weird here. Something is wrong because it doesn't match up. In the other situation you might be talking about, you may find that you assumed that the water only cooled down, but you'll be at like a negative temperature accordingly. So what you would have to do is say, oh, I guess the water cooled and then started to freeze, because otherwise you won't be able to account for all the joules that are there. So as you practice with these problems, you'll find out that the math will start to now tell you that something went wonky, whether temperatures don't match or the total energy doesn't match on either side. That's where you'll get that. Most of the time you should be able to just physically think through, and most of the time you're like, okay, but there may be that rare occasion where you have to go back and you have to check your assumptions. I mean, you're going to be a physicist, right?
Yep.
Yeah. So this whole thing right here about what are your assumptions about your system, look, man, sometimes you make an assumption and it's wrong. So what do? You go back and you try to account for it. You try to put something else in there. It doesn't work. You know, again, and I'm picking on you, Kyra, but Kyra said we're going to heat and we're going to melt. That was her first assumption. She goes through the math and goes, oh, that's weird. It looks like the water's going to have to like cool down a little bit more because it's going to have to warm that icy water up just a little bit more. Then she goes in, she plugs all that in. She goes, oh, wait a minute. I have a number that makes sense. Both of them could reach that temperature. Issa, you've had your quiet hand up for quite some time. Quiet.
Yeah, so I have a pet peeve because you gave a perfect example about how at McDonald's they have this cup and how it would take 30 minutes or so to melt.
Yeah.
In this case, in thermodynamics, will we ever take into consideration time and temperature?
So I do have a neat little take-home homework assignment that I like giving out because I was bored one day and I made up some really funky problems. The answer is no, except for that funky problem. And you'll know if you have to take time into consideration because the amount of power or energy over time would be given to you, and the time would also be given to you about how long you're using that power. Specifically, you're going to bore a hole into an aluminum block using a certain power drill. In general, for this class, aside from some fun problems I give you guys time to work on, the answer is no. We won't worry about the time factor. We're going to assume that the time factor we have allows them to reach to their equilibrium point. If you want to do the time factors, become an engineer. They worry about that all the time. It's just one other level that I don't think we necessarily have to go through on a regular basis, but I do have a fun problem for you just to get your feet wet in doing those problems.
Okay.
And why did you say it was a pet peeve?
Because I mean, how can you be so sure? I mean, if someone were to go to McDonald's in the morning, it's, I don't know, 56 degrees, and then, you know, later in the day, it goes to 80 degrees. I don't know if my soda's gonna melt that quick.
So what I said is nominally. So when these people are doing these calculations, because they do want to do these calculations, because the last thing you want is, first of all, somebody filling up the cup full of ice, because maybe some people, I know plenty of my friends go, give me the soda, no ice, because their soda's already cooled down pretty well and they want all that sugary water. So they say, don't give me the ice, you're jipping me out of my soda. I love a lot of ice, so I'm like, fill the whole damn cup. I'd rather just have watered down soda that's really, really cold than mostly cold soda. But the company itself does have an interest in figuring out, on the whole, for the normal person, how long does it take them to drink their soda? Okay, maybe they're sitting down for a meal. It takes them 20 to 30 minutes to finish their meal, especially if they get their soda first, you know, and they walk away, they start sucking it down, then they get their food. So they take into account how long somebody is going to eat. Then they basically pick a temperature, an average temperature for the average part of the year. And so, yes, in winter, it's going to melt more slowly. In summer, it's going to melt more quickly. But overall, they will say, take a midpoint temperature and say, here's the temperature of my soda. Here's the temperature of the outside. How long is it going to take for the atmosphere to heat up my soda enough to make all the ice melt? And now they've got a warm soda. They don't want to overfill the cups. They don't want to underfill them and make people upset. So they spend actually a lot of time figuring out how this is to essentially maximize their profits. And I know part of this because I worked for McDonald's for a summer. And it was amazing, all these little things that like the manager would like tell me because they knew I was smart. And were very unhappy when I said, well, and I'm done working there because I've got to focus on school. And they're like, no, you're a great worker. And I'm like, well, I'm going to be a better worker when I'm not working here. But yeah, there is a lot, you think that some of these things are random when they're really not. I mean, has anybody else here worked McDonald's? Nobody?
No.
I'm
So-
reading Fast Food Nation right now, though.
So that's not where I was going with this. When I worked McDonald's and I was back on the grill, I worked the 10-to-1 grill, which is basically making your hamburgers, cheeseburgers, and Big Macs. And so it's called a 10-to-1 because you can get 10 patties down per one row. When you pull these things off, have you ever wondered like how they always seem to get the same amount of ketchup and the same amount of mustard? There is a machine, a little thing you hold in your hand that as you go over the bun, you press a switch and it gives you the precise dollop of how much ketchup you're supposed to do or how much mustard you're supposed to do. And they spend a lot of time researching just how much people in general want for ketchup and mustard on their burgers, and they designed this apparatus so that as you go over each bun, you just go thump, thump, thump with your thumb, and it goes squirt, 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 the exact amount every single time. Again, so they don't have people's heavy hand on the ketchup, or now we lost money on ketchup or mustard or the like, or someone going, there's not enough mustard. They did a lot of taste tests, a lot of research to say, in general, this is how much we should do. Let's do it. And on the whole, everyone's going to be happy. And we've minimized waste and maximized products. Profit. Thank you. So yeah, there's a lot of thought that goes into these things, believe it or not.
Yeah, McDonald's is like super heavily engineered.
Yeah, it is. It really is. So I hope I've gotten rid of your pet peeve, Isa. I didn't mean to trigger you.
Oh no, it's fine. I was just like thinking you can't be so sure that it's only going to take 30 minutes depending on the temperature, the seasons, and the time of the day.
Right. And again, all of those are approximations, right? So,
Yeah.
But yeah, they basically go for the overall holistic approach, such that in general, and I think that's one of the reasons why a lot of fast food joints, you're too young to remember this, but it used to be that they didn't have soda machines out in the lobby for you to just do this. You had to go up to the counter and ask for more soda or more ice or whatever. They didn't always have the soda machines out front. But now they've started to do that outside so that people can just regulate themselves. And they've said, forget it for the profit. But I mean, if you think about people coming through the drive-through, they still have that mechanism in place such that on the whole, people are going to be happy with their experience eating there. Oh my gosh, that was one of my most epic side stories ever. That's kind of cool. All right. Okay, how about this? Ready for my longest prompt ever? Here we go. I love this one. It is 1864, and you are a blacksmith. And you are a blacksmith.
The hell's a blacksmith making in 1864?
Okay, here we go. You are quenching your 2.5 pound horseshoe into water to harden it. So you can imagine a blacksmith taking a bunch of iron, shaping it into a horseshoe. It's glowing red hot. Then they plunge it into water. That's not just to cool it down. It actually has a materials benefit of hardening it. By quenching it very quickly, you force those red hot grains of steel to stop and arrest their growth very quickly, and that will harden the steel. If you want to talk about hot rolled and cold rolled steel and the things like that, talk to me after class. I loved my material science class. It was really cool. All right, but this is what you're doing. You're 1864, you're a blacksmith, you're quenching your 2.5 pound horseshoe into water to harden it. When you plunge your horseshoe, into a 5-gallon bucket of water at 77 degrees Fahrenheit, the water heats up. Water heats up to 90 degrees Fahrenheit, and 0.35 ounces of steam rises into gentle spring air. Ready? How hot was the horseshoe? How hot was that blacksmith getting that horseshoe to shape it and make it work? Okay. Who wants to do this problem, Ben? Huh? Oh, looks like you just volunteered. I love tricking people into volunteering. All right, so what do we need to know? What information do we need? Well, let's take a look first at our system. What do we have here? That means you, Ben. Keep your Issa, is your hand still up?
My bad.
Oh, no, that's fine. So Ben, you're on deck, so don't mute yourself. We're working through this here. What are the pieces of our system here?
So we got the horseshoe and water.
All right, we got the horseshoe, and we have the water. All right, what is the horseshoe going to be doing?
Losing energy.
Right, it's going to cool down. All right, and that is an MCP delta T. Okay, what's the water going to do?
Gain energy and also lose mass.
Right. So it's going to heat up, and that's an MCP delta T, and it's going to vaporize, right? Now I'm going to assume here, I'm going to assume that 0.35 ounces does nothing to the 5 gallons worth of water in this situation. So because I have Dallas in the room, note, neglect loss of mass of water due to steam. We can do it, but there's no point. Okay, so now that we know what's going on, we're going to need some information. All right. Just getting that real quick. 0.46. Wait, is that right? 0.46? Yeah, 0.46. Okay. What information do you want, Ben?
CP for the horseshoe, delta H for the water vapor, and CP for liquid water.
Okay, so I'm going to assume that my horseshoe is made out of iron. So the heat capacity of iron is 0.46 joules per gram degree Celsius. The heat capacity of water is 4.186 joules per gram degree Celsius. That delta H of vaporization was 2230 joules per gram. Is there anything else you want to know?
I don't think so.
How much is 5 gallons?
Hey, now we're starting to think. We need 5 gallons, right? So let me give you the other ancillary stuff. Ancillary conversions here. Okay, so 5 gallons is nominally 18.9 liters. 0.35 ounces is essentially 10 grams. 2.5 pounds is 1.14 kilograms. 77 degrees Fahrenheit is 25 degrees Celsius. And 90 degrees Fahrenheit is 32 degrees Celsius. I think that pretty much covers what we need, yes? Okay, the horseshoe is going to be losing, so that's the one that's going to be negative. The water is going to be gaining, so that's positive. So what we have here is just setting these things equal to each other. Let's take a look at the horseshoe. All right, that was an MCP delta T for iron. And so what do we have here? And that's going to be a negative, right? Because that's one losing. So we have the mass. What's the mass, Ben?
14.
1,140 grams, is that what you said?
14. Unless I wrote that down wrong.
1.14 kilograms is 1140 grams.
I wrote down 1.4.
Okay. And then we need our heat capacity, which we said was 0.46. And what is our temperature change? Ben?
We don't have T initial. That's what we're looking for.
Okay. Do we have anything else though?
Can we assume that the iron goes to 90 degrees Fahrenheit, the same temperature as water?
That's the whole point.
Okay.
If we don't make that assumption, we can't finish the problem. So we have now the 32 degrees Celsius minus the initial temperature. That's what we were starting to look for anyway. So we'll take that into account. So let's go ahead and do some multiplying here through. I need the 1140 times 0.46 if you could. I believe that's going to be somewhere around 500.
It's 524.4.
Okay. So you got 524.4. And what I did there, I had her do these guys because I'm going to multiply that by my initial temperature. I should note actually my units before I do that. So my units would be in joules degrees Celsius times the initial temperature. And since it's a negative times a negative, it becomes positive. Okay. And then I need to multiply that by 32.
16,780.
Okay. So right now we have our horseshoe. Let's look at our water. So that's an MCP delta T for water, and the M delta H of vaporization, and that's going to be for our steam because our masses will be different. So there's one little thing, Kimchi. You wanted to know how much 5 gallons was, and I told you 18.9 liters. So what does that tell you it is?
It's 18,900 grams.
That's right. This is now 18900 grams.
Also, I got a different number when I multiplied 524.4 by 32.
It's 16,000.
16. Thank you.
Yeah.
Did I misunderstand you?
Yeah.
Okay. Thank you. Okay, so for our water, we had, what was it? 1890 grams. And remember, all this is positive, right? So we have 1890 grams times the heat capacity of 4.184 joules per gram degrees Celsius. And what is our temperature difference there, Ben?
Still working on it.
Well, you can just give it to me numbers wise, right? We know where we started and we know where we ended. We end at 32. So that was the 32 degrees Celsius, and we started at 25 degrees Celsius.
So we get a difference of 7.
Right. So that one we already knew the beginning and end part. And now we need the steam, which we said was 10 grams, and our heat capacity of steam, which was, our delta H of vaporization, sorry, which was 2230. All right, since all of that is numbered, what is that number? And since it's going to be slightly different because of the numbers I was using, actually it's going to be more than 55. What do we have?
57,5843.
Yeah. That's a whole lot of going for it. Okay, so now we just have to put these two things together. So we equate them. So we now have, so let's see, equate them. So now we have 524.4 joules per degree Celsius times that initial temperature minus 16780 joules is equal to 575,843 joules. So if we just did that one more time, it's 524.4 joules per degree Celsius times the initial temperature. And do we have a number for pulling those joules over?
592624.
Okay, so what is my initial temperature then?
1130.099.
So 1130 degrees Celsius. Or, since we are blacksmiths, roughly, well, I guess we could actually do that. So let's do that to Fahrenheit. Where's my calculator? Fahrenheit is 9/5 C, so 9 divided by 5 times 1130 plus 32. Is that 2066?
Yep.
Because we are, 1864 or blacksmiths. Does that seem like a reasonable temperature to get a piece of metal up to?
Forrest,
Yes.
I'm kind of confused why some steam was made when it only went up to 90 degrees Fahrenheit.
Well, have you ever taken something stupid hot and dumped it into water?
Yeah, and
Yeah.
steam.
It's going to steam up, right? So, yeah, again, I get what you're saying. You're like, wait a minute, shouldn't we take all those 19 liters, heat them up to 100, and then try to vaporize them? Sure, if that's what you were doing. But we're taking something stupid hot, we're dropping it into water. Some of that will actually just, bam, vaporize, bam. And so, again, sort of experience would say, no, you can just vaporize something like that. You absolutely can. You can go straight from that and go and just do it. And we don't have to worry about the heating up of that little 10 grams from the 25 to the 100, and then it just goes.
Okay.
And so I just wanted to point out that this 1130 Celsius is actually a reasonable number here because the melting point happens to be 1500 C. And it turns out, if I'm not mistaken, we should be at about 2/3 of the melting point. So 1130 divided by 1535. So about 75%. In this range, by the way, is exactly where they would actually want to do this sort of annealing process and hardening process. And so it makes sense that we would get close to that. So if you ever get to a materials science course, you'll learn that they wanted to get it close to this range of temperature. It allows for the shaping of the metal as well as the hardening of it. Do we have any questions on that math or what's going on? Or is it just kind of like, okay, I get it. We're basically number crunching.
I got a different answer for the blue.
Hold on, say it again, Shauna.
I got a different answer for the blue. Can you just scroll up, make sure I plugged everything in right?
I did too. I got like 576.
Yeah, I got 576505.
Well, who are we gonna blame?
Ghostbusters.
No, blame, calling Ghostbusters. So we can still do this. What was it, 5-7?
6505.
Okay, I blame you, Ben.
Fair.
This is fair. I like, he's like, whatever. Okay, then do the math again for me.
Oh, also you wrote the TP as 4.184.
Oh, shoot. I have no idea where 4184 got stuck into my head because for 4 years, all I had to write is 4.186 over and over and over as a chemical engineer. You would think that would be burned into my brain, and every now and again, an extra 4 shows up. I don't know why. Keep me honest on that one. That one's going to be a slip up I accidentally make, and I have no idea why I do it. So what's my new thing over here? Right here, what am I putting in?
576107.
576107, which changes my temperature to. Which changes my temperature to.
What?
1098, 1099.
I got 1087.
Oh, 1087. Did I 557? That is impossible. 576107 divided by 524.4. I get 1099 essentially.
Yeah.
Okay. Which basically makes it 2009 Fahrenheit. Okay, so now that we've got math, now let me see. Who are my frenetic ones that are going to freak out? Chef. Who else is going to freak out? Maybe a little Mang. Ramirez. Isa. Yeah. Kyra. Listen, at the end of the day, if you had 1087 and I had 1099, I'm going to assume that there were some rounding errors because these things will happen in here depending on how many decimal places you want to keep and such. Dallas, don't worry about it. If you had 1099, 1098, 1087, if you had 1400, I'm going to start checking your work and being like, all right, where did they screw up? If you're not getting exactly these numbers, you may be leaving numbers in your calculator and just continuing the calculation, and that's totally fine. It's not going to make that big of a difference in the grand scheme of things. So I don't want you guys to get caught up in the minutia of having exactly this number because small rounding errors will occur as we have to keep track of the fact that we're doing calculations and not leaving it as one gigantic solve for X and plug everything in because it's just too hard to keep track of all that if you're doing it. So this way of actually plugging in stuff and figuring out, oh, you can't see what I'm doing, plugging in stuff and getting a number and plugging in stuff and getting a number. Of course, we rounded this 524.4. Of course, this wasn't exactly 16,080. That's going to be okay. In the end, you will always be close to the actual answer as long as you haven't done anything wrong. Does that make sense, guys?
Yep.
Yeah.
Yeah.
And did I pretty much pick all of my frenetic ones that would freak out over that?
Yeah.
Yep.
Did I miss anyone? Oh, I love the fact that I get to know you guys. All right. I think brain is full for today. What do you guys think?
Definitely.
Okay. Any more questions before I stop the recording? Seeing no hands. Stop the recording.